Yeah, so last time we did the measurement exercise, we calculated our standard deviations, and then at the end, we had 6 or 7 different groups, and I showed you about the pooled standard deviation, where you just do a weighted average of the variances, and then you can add together and sort of average everybody's standard deviation if you have multiple groups. I think that would be a really neat thing to do in quant, to kind of add what's the standard deviation, the pooled standard deviation for this lab. It'd have to be the exercise after you do the titrations, and you can see how good or bad the whole lab section is. And anyway, we could do a Hogwarts trophies or something between the lab sections. Which section has the best, which house has the best standard deviation? And so today we're going to see what we do when we have a standard deviation for a measurement, a series of measurements or an experiment or a technique, and we then have to do a calculation with those results. So it's very easy to titrate 3 times, 5 times, and calculate the molarity. And then you've got 5 versions of the molarity. You take the standard deviation, you know what your uncertainty is. But what if you then use that molarity in other calculations? How does that uncertainty end up in the result? And so this is called propagation of uncertainty. We're taking the uncertainty in our measurements and propagating it through to some computed result, just like you did in CHEM for like the carbon monoxide bond length, right? You had uncertainty in your peak picking positions and so on, and you did an ANOVA table, and you got the rotational constant plus or minus some standard deviation, okay? But then you had to compute the bond length, and the bond length was the square root of that number. So what happened to the standard deviation? What do you do in that situation? Well, when you take a square root, it's 1/2 of the relative standard deviation, and we'll see that today. Okay, so that's propagating the uncertainty. You have a measured result with its uncertainty, and then you do a computed result, and you need to calculate the uncertainty of the computed result. And so this is the basis of these things. We want to compute that or propagate that uncertainty because a numerical result without an estimation of its uncertainty is useless. Okay. I mean, I could guess at the bond length of carbon monoxide and give you a number, or you could measure it and give me a number, but with neither one of us giving an estimate of the uncertainty, we're not telling somebody how sure we are. And so they really have a hard time trusting our results if we don't give them an estimate of the uncertainty. And your results, especially in the forensics situation, is all about trust. So all of this statistical stuff isn't just so that we can learn how to do statistics. It's about trust and how you can convey how much you trust your own results. Like if you say, well, the answer is 2 plus or minus 1.8, you're not very confident in that number. Okay, but if you say the answer is 2 plus or minus 0.03, now you're very confident in it. And so these directly measured quantities have easily determined uncertainties. Like a 4-place balance, you can read on the box when you unpack it, it says it has an uncertainty sort of in the balance of performance of plus or minus 0.0002 grams. Okay. Now you can still take multiple measurements with that and compute your own standard deviation, but a single measurement on a balance would give you a very good, very certain result. Now multiple measurements then incorporate other uncertainties, and so we calculate the mean and standard deviation. Review question, when do we use the mu and the sigma? That's conveying something. So if I give you a mu and I'm not communicating to you about the measurements that I've done and so on. Yes? A population. And so what's our sort of cutoff for a population? 15 or more measurements. Yeah. So you've done a lot of measurements. 15 is a lot. Okay. Think about if you're doing titrations. Who wants to do 15 titrations? Nobody. Yeah, you'd use up all your standard. But anyway. Okay, so then here's the math. Someone has done this for us. It's really nice. It's in the analytical books. They've gone through and done the partial differential equations on all of these situations, like if it's a sum or if it's a multiplication or what have you. And so these are the results of derivatives. So this is the slope with respect to A and B and C in this term. So how does Y vary? Well, it varies according to the slopes or the uncertainties in A, B, and C. And so that's what we have here, these equations. So these are the scenarios that you have to diagnose when you're calculating your uncertainties. And so you have situations where there's sums. And so when we're doing, volume measurements or mass measurements, typically in a graduated cylinder, we have volume measurements, fill it up to a certain mark, write it down, we deliver something, go back and read the next mark, and we take a difference. So we've got two measurements in that situation, and so that's going to be a sum or a difference. Products, that would be conversions of, say, this molarity and this amount. You calculate the number of moles or the mass in a result. Those are typically products. And so we have different ways to propagate those uncertainties. If you'll notice this equation here, this is giving you what you want. You want the uncertainty in Y, right? So this is our result Y, and we want to know the uncertainty in Y. And so these squares, so sigma squared is called the variance. And so this equation is captured in this very small, simple shorthand. This is the smallest way to write it. It's just the sum of the variances. The variance of Y is the sum of all of the variances, excuse me, that go into that sum or difference. And it's interesting. Notice that even though we're subtracting C, we don't subtract any of the variances. The variances all add. So, if I'm taking something away and I have uncertainty in how much I took away, then there's going to be uncertainty in the result, just like if I was adding something and I was uncertain about what I was adding. Look at the sort of the symmetry of that equation with the one in products. Okay, if I were to move Y back over to this side, I would have sigma Y over Y, and if I got rid of the square root, I would have this squared, right? So I would have this shorthand equation here. And so it's the relative standard deviation of Y squared is equal to the sum of all of the RSDs of the pieces in that product or division quotient. And so see how these are very similar equations, but one uses the variances, and the multiplication and multiplication and division uses the RSDs squared. So you should be able to use these and really memorize these two and be able to use them. Now, an exponent is a special case of multiplication. And so you can get the exponent one. If you know the multiplication one, you can get to the exponent one. It's very, very similar, okay? And then the logs and antilogs, we're not really going to use those in this course, but I have a couple of examples in this note set. Okay. And so let's look at an example. So here's an example, say, from a lab that wants to know the identity of this metal substance, and so they're going to use density to identify the metal substance. So they have a metallic object weighing 2.503 grams, plus or minus 0.225 grams, so that's the uncertainty in that measurement. It displaced 0.13 milliliters, plus or minus 0.05 milliliters of water. So we use a graduated cylinder. You make the mark, you drop the metal object in, you make the new mark. That difference is 0.13 mils. And then you have the object weighing 2.5 grams. So what's the density? That's pretty easy. Density is mass over volume. So we can take the 2.503 grams and divide by 0.130 mils, and we get our density 19.2538462. That's all on our calculator. We're going to keep all those digits for now, just as guard digits. And then the second question is this gold or tungsten? Now, it would be pretty easy to look at the two, because gold is yellow colored and tungsten's kind of a dirty gray. But let's say we can't do that, okay? So we're just going by the density only. And the gold is 19.28, and the tungsten is 19.25 grams per mil. So which is it? Are y'all shy, or is there a reason why you're not answering? Tungsten? A couple of votes for tungsten? Tungsten, raise your hand if you're for tungsten. Okay. That's the majority. What about gold? Anybody that's going for gold? Okay. What about the ones who are saving their conclusion for later. Very good. Okay, so this is a good thing. Those two people that raised their hand and were bold enough to say, "I'm saving my conclusion for later." Can anybody articulate why you're hesitant? Why are you hesitant?
So in this case, the uncertainty within the hundreds place is beginning to where it could be 0.28 or 0.25. We don't know.
Yeah, so we don't really know yet. And so that's good to kind of hold off. We don't know what the uncertainty is in that result. So we have to propagate the uncertainty from the two initial measurements into the result. And then we'll get a feel for whether we can make a judgment whether it's tungsten or gold. Okay. So let's propagate that uncertainty. So here's our equation. So when in those earlier examples in your notes that says y equals a times b over c, you know, that's this situation. So in that case, on the little slide, y is our density rho. So that's our result. And on those little equations, that's y. And then the a times b over c, we just have a and c. We have 2.503 divided by 0.130. So we only have two terms in our multiplication, not three. And so then we set up that deal where it was y times the square root of the RSD of a squared plus the RSD of c squared. And so that's that equation right there. So let's put all these pieces together. So here's our equation that we're using. And so this initial y part is right here. So that's our result. I'm keeping those ridiculous numbers of digits just to make the point that we don't want to round yet. And then the next one is just the numerator. And it's the uncertainty over the value. So this is the relative standard deviation, the standard deviation of that measurement divided by the measurement. So that's our RSD for the 2.503. And the next one is the RSD for the 0.130. 0.5 over 1.130. So this is now going to calculate the uncertainty in our density measurement. So it's 7.6 grams per mil. Yeah, 7.6. So if we were to write this out, plus or minus our standard deviation, our result would be 19.3 plus or minus 7.6 grams per mil. So this is giving us an idea of our significant figures, right? We're keeping two decimals or two places of uncertainty just because that's a convention. This has to match that in terms of its place value. So since we have 0.76 or 7.6, we're going to put that here, and then that's going to tell us where to round this number. So we had all of those digits, but we're going to round to the tenths place. So right here is a 5 following the 2, so we're going to round up to 3. So 19.3 plus or minus 7.6 grams per mil. And so let's look at this in terms of our uncertainty values. So our RSD for our volume measurement, so here's our volume measurement, it was 0.130 plus or minus 0.05. So that would be sort of the distribution of our volume measurement. And our distribution of our mass measurement, it was 2.5, and the RSD was narrower relative to that number, 0.225. And then our result is 19.3 plus or minus 7.6. Okay. So this is telling us that the sort of the widest distribution dominates, right? The least certain part of our calculation is destroying our confidence. You can look at this too. Let's go back to this this right here. Which one of these is larger? Let's just get rid of all these extra digits. And can you see that that's 2 over 25? That's 2 over 25. I can move the decimal places. So everybody, I just want you to look at that ratio and say, okay, that's two parts in 25, 2 over 25. What is this one? 5 over 13. That's a much bigger value, even though 0.05 seems like a smaller number, and it is a smaller number than the 0.225, but it's relative to the measurement. And so we're uncertain of 5 in 13. Here we're uncertain in 2 out of 25. And so this is going to be the dominant error. And so this also tells us our volume measurement is what's killing us in this determination. So this error analysis, one is the goal is to propagate the uncertainty and get that value, okay? The second goal of uncertainty propagation is to analyze what in the lab needs to be improved to make this a better measurement. Now, we could spend a lot of money making a better balance, but if we don't change the volume measurement, this is still going to torpedo our results. It's this thing that's breaking our confidence. And so we need to go in and look at our volume measurement and get more precise on that. So this is our conclusion. Our process stinks. So this is the density that we measured, 19.3 plus or minus 7.6 as a standard deviation. And so our 50% confidence interval is this green, okay? That's our 50% confidence interval. And it contains all of these metals here. It could be tantalum, tungsten, gold, rhenium, platinum, osmium, or iridium. So let me tell you what that means. That 50-50 means it doesn't mean that it's a 50-50 chance that it's say gold and a 50-50 chance that it's tungsten. It's saying there's a 50% chance it's one of these. I cannot tell you which. And there's a 50% chance it's not one of those. So it's either one of those or it's not. Flip a coin. So that's really bad, yeah. And tungsten and gold are so close together, there's no way we would be able to tell the difference between those two. They're in the 50% grouping, though, but it's just as likely that it's one of these other 6 elements or 7 elements. Now, what about our 95% confidence interval? I mean, we have a measurement, we have its uncertainty, so we can stretch this out. If we bring that, there's sort of a 2.5% chance it's down here. There's a 2.5% chance it's above here, okay, even though no metals exist up there. And then there's a 95% chance it's one of the metals inside this green block. And these are all the metals there. So I'm 95% sure it's one of those, okay, with this measurement. So it doesn't sound very useful. In fact, it's useless in determining between gold and tungsten. And it's useless in determining between any of these. But what about these? I'm 95% sure it's not magnesium, okay, or one of these metals down here. So it is somewhat useful. The really non-dense metals I can exclude. So even though I have a really crummy process, if it measured to be that dense, 19.3, even though I'm uncertain, plus or minus 7, I can be 95% sure. Actually, since it's all on this side, I could be 97.5% sure that it's not one of those lower density metals. So it's not completely useless. And so you could say, yeah, but the math worked out so that the number was closest to tungsten, 19.25. And, your kids, you say, well, did you pick up your room? Yeah, but you asked me to do such and such. And so I always wanted a hat that said, my name's not yeah, but, because they always say, yeah, but this, yeah, but excuse. Yeah. So there's no yeah, buts. And, you got to go with what the numbers tell you. And that's important, too, because if you're going to go in front of a court and you're going to be cross-examined, you need to be able to rest on something that's objective, not subjective, not something you wanted, but something you measured. And that way you're standing on solid ground. So now let's do a calibration curve example, because this is very, very related to working in the lab and so on. But let's go back. Were there any comments or reactions to this or anything I could clarify? Because we're about to shift gears. Most students run into trouble right here. They finish the result. They have no problems with that because that's just, you got the density equation, mass over volume. I'm confident you guys could do that. You get to here and you're like, which equation do I use? That's where I think, when I get questions on the homework, they're like, okay, I don't know which equation to use from this little page right here. Okay, and so focus on the operations that you're doing. And sometimes you have a combination of these. So in this case, we had a product and we had a quotient. Okay, so that's why we had to use that equation. So we look over here, like multiplication and division. So that's the equation I use, and then I've got to do the relative standard deviations of all my parts. Good? Okay. Okay, so now let's look at an external calibration curve. So external calibration means we have external standards to our sample. So we build up external standards, we run several of those. In this case, we did 5. So we have a concentration or an abundance, parts per billion of cocaine. Think, 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 we run our standards. We measure the area counts of a chromatogram, and we get our calibration curve. It's a beautiful one. Look, 3 nines. I mean, that's beautiful. Okay, nice straight line, pretty good range. You know, we're going from, you know, around 10,000 up to 250,000. So it's got a good dynamic range and a good range of concentrations from, you know, that looks like maybe 20 or 10 all the way up to 500. So that's a good range of concentrations too. So it's a great calibration curve. And so then we measure 3 unknowns. And when we measure those unknowns, what do we get? We get the Y signal. We run them through the chromatogram, count the area under the curve, and we get three of those. But I'm not interested in area counts. I mean, I could take those 3 measurements and calculate a standard deviation, right? That's easy. But then I calculate my concentration, and what's the uncertainty in my concentration? So these come across that we use that equation. You know, if it's Y equals mx plus b, we solve for x. So it's y minus b divided by m, and we get our x values. And so we can get our 3x values. Now you could do that, you know, straight away and just calculate your 3x values for each of the y values, and you can do a standard deviation. Okay. But I'm going to show you how to get there with propagation of uncertainty using this equation. Okay. So this trend line is not useful for propagation of uncertainty, because I have m, the slope, and I have b, but I don't have the standard deviations of those. I don't have sm or sb. And so I need those. And to do those, you have to do the full analysis of variance. That's what ANOVA stands for. Write that up. So, A. So you see how I spelled it kind of funny, because it's analysis is the AN, O for of, and VA for variance. That's ANOVA. Okay. I don't like that, but I didn't make it up. So, so you go to the ANOVA table, and you get this full table here out of Excel. So how you do this is you go into Excel. You guys did this in PChem, but you go in and you have your Y values and your X values, and you put those in, and then you hit regression to determine if the intercept is going to be used or not. In this case, we use the intercept. We get our R squared value, which should match our trend line. We get these values here, the coefficients. Those should also match the trend line. But this is the beautiful thing from the ANOVA analysis, is we get the standard error in B, and we get the standard error in M. So we get our uncertainties in both of those. And so then we can do propagation of uncertainty and calculate the uncertainty in our X values. Given a Y value, we can calculate the X values. And so then we have a new calibration equation, which is the slope plus or minus, and then the intercept plus or minus. So we have all of the things we need. This will also tell you if your intercept is valid or not. So while we're here, we're going to get into this a little bit more. And in this case, our example shows a problem here. So this is a problem that we will fix later in a future lecture. Okay. So this slope should actually be set to 0, because the p-value, the probability that it's 0, is 48%. There's a 48% chance that slope is not statistically valid, that it's just 0. And so we'll fix that in a future lecture. So given a y value, what is the uncertainty in that y value, and how do we find x? So Here's our M, our SM, so those came from the calibration equation and the ANOVA table. And here's B and SB. And so let's say we run 3 check samples. Now we have this true value here, 125 parts per billion. So I'm going to call that XT for our true value. And so what we're doing is we're checking our instrument. We've got a known. We're running it through as if it's an unknown, and then we're going to see the result. We'll get hopefully 125, but we'll also see how certain we are. So this is the average 55,333 counts, and here's our uncertainty in that value. Okay, so we can do a Y bar if you want. Y bar. And so what is X? Well, let's solve for our concentration. So here's our equation, Y equals mx plus B. So we take B and subtract it from both sides and divide by M, and we get X. So here's our X. So 129.9 parts per billion. So we're not at 125. Rats, let's go home. Okay. But how certain are we? Right? Maybe our error bars contain the true value because it's 129.9 plus or minus something. And so if it's plus or minus, 95% confidence intervals and that contains 125, then we got the right answer. It just didn't happen to hit 125 numerically exactly. But if our uncertainty is such that it contains a true value, what more could we ask? Right. So what's our uncertainty in X? Well, we're going to use this linear fit equation and calculate that uncertainty. So this is the issue. Which of those uncertainty equations do we use? Remember, we had some options. We had the sum option, y equals a plus b minus c, and we had the products and quotients option, a times b over c. It doesn't fit in either one of those boxes, does it? Anybody have a game plan? Yeah, do it in parts. Just like we have to do the calculation in parts, right? We typically would add those two numbers first and write it down, or your calculator holds it in memory, and then divide by the other one. So we're doing the calculation in 2 parts. We're going to have to do the uncertainty calculation in 2 parts. So we're going to calculate the numerator, and we're going to get the uncertainty for the numerator. And then we're going to do the products quotients piece and calculate the uncertainty in the result. So this is a subtraction piece, and that's a division piece. So we're going to do it in 2 parts, just like we did the calculation. So the numerator, we're just going to call it numerator, y minus b. So let's take that, 55,333 minus 1214. So there's our numerator, 54,119. So that one you probably have to write off to the side. There's your numerator. And then we're going to calculate S-num, the uncertainty in that numerator, using the variances. We're going to square the uncertainties in Y and square the uncertainty in B, add them together and take the square root. And that would be our uncertainty in the numerator. And I've used subscripts for you just so you can keep track of what's going on. Okay, so there's our uncertainty in the numerator. 1532 counts. Okay. And the units will work out. If you keep the units and keep track of the units, then everything's going to be nice. Okay. Now we calculate with the products one, products and quotients, we calculate this. But notice how we're using the numerator and the S numerator, not Y and SY. So this S numerator goes here. That's the RSD for the numerator. And then we have the M, which is the denominator. We have SM over M. And so then we square them, take the square root, and multiply by X, and we end up with this result, 4.1 parts per billion. So that's pretty good. So that's how you use a propagation of uncertainty in a linear fit. Okay. It should seem easier the first time you go through this. The second time, if y'all did do any of this propagation of uncertainty in quant, then this is the third time you've seen it, because we had a video on it in PChem, and now we've gone through it in detail for this. So that's typically the learning curve. 3 exposures then it's yours. Do you remember your old English teacher? If you learn a new word, use it in a sentence 3 times and it's yours. Yeah, same kind of thing with math, anything that you're learning. If you're exposed to it 3 times and you have to do something with the information 3 times, then it's yours forever. So don't talk yourself out of it. A lot of people have this negative self-talk. Oh, I didn't understand that the first time I saw it, so I'll never get it. Don't do that, right? If you say you'll never get it, you're right. Okay. So let yourself get it. It's not that bad. You just got to know those equations and when to use them. Okay. So here's our plus or minus. We just use plus or minus a standard deviation. Okay, that gets us down almost to the check value. If we did plus or minus a 95% confidence interval, which is roughly 2, it's 1.96 times that, then it would be plus or minus 8. And so that would definitely contain our check value. So, hey, we did well. Okay, so we got our check value within our 95% confidence. Anything I can clarify on this one? This is the most complicated example that we're going to do. Although, I think there's a video where I do it for the quadratic equation, and there's a bunch of parts to that. Yeah, it's ugly. Okay. So what's causing these errors? We're sort of specifying a difference between gross mistakes, like tipping over a beaker or having a bubble in your pipette. If you got a little speck of dirt or something in your pipette and you suck up the liquid and you don't notice that there's a little air bubble on the side of your pipette inside the tip, and you keep using that for serial dilutions, you're going to be off on every one of them. Okay, that's going to introduce a bias. That's a gross error. That's a substantial error. I guess it depends on how big the little air gap is, but this is also talking about tiny little random fluctuations. I mean, if you're doing a chromatograph, that's a very complicated instrument. There's hundreds of little variables that could go up or down at any different run. Y'all ever use the Spec 20s? Right? Your Spec 20s, you got one light bulb, you got one sample, one detector, you put your blank in there, you measure that, you zero it out, okay? And then you take it out and you put your sample in right when somebody gets in the air, in the elevator, and the whole voltage of the building drops ever so slightly, and the bulb gets a little dimmer, and you think your sample is absorbing more light than it actually is. These are little things that can happen that you would not be able to control for. Okay, and so one measurement is with the elevator running, one other measurement is with the elevator not running. And so there's thousands of little variables that are out of your control. And if you add in those fluctuations, you eventually arrive at this normal Gaussian shape, this normal distribution. So that's the result of millions of uncontrolled tiny little variables that bump your measurement up or down. So that's what's going on. And so that's why we use this confidence interval. We expect that Gaussian curve from all of our measurements. Okay. If it's not a Gaussian curve, then there's a systematic error in there somewhere. There's a bubble in the pipette tip, or something's wrong with your balance. Okay. But if nothing is wrong with anything and you just have minor fluctuations, then you get that nice normal distribution curve. Okay. And so we take our mean and we add plus or minus a certain amount to calculate the area under that curve to capture all of the results. If we kept doing this experiment over and over again, our instruments working well and so on, we would get something that contains that 125 parts per billion check sample that we used. And so this is telling us that everything's working well. And so these areas under the curve, if it's plus or minus 1 sigma, so these down here at the bottom are standard deviations. If it's plus or minus 1 sigma, that's covering an area of 0.683, so that's 68.3% confidence. Close to 70. So a lot of times we use that. We'll just say, plus or minus 1 standard deviation, but that's your 68% confidence interval. Okay. It doesn't really roll off the tongue. We like 95, right? And so 95% confidence is plus or minus 1.96. So memorize that one. Because you're going to use it so often. That's your plus or minus standard deviation for 95% confidence. It's very close to 2, but if I did 2, it would be a 95.4. Okay, so I guess we're being precise here. And so 1.96 gives you exactly 95%. Plus or minus 2 gives you 95.4. We could go to 99.7 as plus or minus 3. So plus or minus 3 sigma is 99.7%. So this is the result of our measurement. So the center of this would be mu, and the spread is our standard deviation. So this would be the curve of all of our measurements. If we did this chromatographic experiment, many times, more than 14, we could plot out this frequency curve. And so what we're saying is that xt is somewhere inside here. So we're saying the true value that I don't know is somewhere inside these limits. Now, in our example, we put in a check value, but if you're doing a true unknown, you look at your standard deviation, you're like, well, these are the statistics. We don't see any gross errors or whatever. Then our true value should be within these limits. Okay. So that's a range of values derived from a sample statistics that are likely to contain the true value of an unknown quantity. So that's what a confidence interval is. And it's not 100%, it's 95%. So out of 20 measurements, you expect one of those to miss the mark. 1/20th is 5%. So you expect to miss the mark 5% of the time. So that's 19 out of 20. That's pretty good. It's not great, but it's pretty good. And so this range of values is derived from the standard deviation and this normal distribution function. So that's how we come up with these plus or minuses for our confidence intervals. Okay. So let's think about this practically. even 95 or certainly 99% confidence stinks. That's 20,000. So even 99% confidence, that's 20,000 lost articles of mail per hour. That's not good. I don't want unsafe drinking water 15 minutes a day, and I wouldn't know which 15 minutes, right? Or 5,000 incorrect surgeries per week, or 2 long or short landings at most major airports. I don't want that to happen, okay? Or 200,000 incorrectly filled prescriptions every year. Or in the forensic situation, 16,204 murders in the U.S. 99% confidence would yield 162 wrongful convictions. And so that was just from 2008. But so we got to do better than 95% confidence. I mean, in quant lab, 95% confidence, that'd be great. You're just doing titrations and so on. You're like, okay, I've got this. But nobody's liberty is at stake. So how do we get this better than 95% confidence without having to do 1,000 measurements and really narrowing our uncertainties and working with gold standard everything? We use multiple experiments. And so if you have a chromatograph that tells you where cocaine comes out, and you have that calibrated and it's plus or minus 95%, then you're pretty confident in it, but 95% is not good enough. And then you have a mass spec that measures the mass of that molecule and says it's cocaine. And then there's a plus or minus on the mass fragment or whatever that you're using to identify, and it has 95% confidence intervals. Okay, now you've got two measurements, and to get through both, it's called a Swiss cheese problem. You know, Swiss cheese is full of holes, and if you've got all of your instruments lined up, can there be a hole that goes through both instruments? Is there a Swiss cheese hole that could fool the chromatogram and fool the mass spec? And the chances of that are really, really slim. So that's how we get around the 5% chance of getting around the chromatogram. We have to have multiple instruments or multiple techniques or a spot test too. The spot test isn't easily quantifiable, but it's a Swiss cheese, and it's got a hole over here that's not going to line up with the chromatogram or the mass spec. Okay, so spot tests are very valuable. They're just not quantifiable, but you better do them. It's a good idea to do them because that's another block of cheese with a different hole in it. And so you would have to have a sample slip past the spot test, slip past the chromatogram, and slip past the mass spec for it to be wrongful result for cocaine or something like that. In fact, it's so unlikely, we start questioning the analysts if that happens, because the analyst is less reliable than those three techniques having a result where it slipped past all three. Okay, we start looking for dry labs and things like that. So what confidence do we want? Well, this is the same, not just in forensics labs, but also automobiles and airplanes and all kinds of high quality manufacturing. And so they've developed this term or this structure for uncertainty management called 6 Sigma. And the idea is that you want to be 6 standard deviations away from your false or specification limit. So let's say here's our mean and here's our standard deviation. We want 6 of those standard deviations to pass before we get to our lower specification limit. So let's say this was, say, a detection limit for cocaine, and we'll do that with our trainee and our forensic chemist examples in a future lecture. We'll look to see how likely it is for a trainee to give a wrong result versus someone who's doing the training. And so we'll look at the specification limits and see when we would have a false positive or a false negative. And so that's what this is about. And it's sort of the gold standard for quality. Now this, you can't maintain a 6 over long-term operation typically, and so they will relax it to 4.3. And it's also not a particular end result, it's per opportunity. So think about an automobile and how complex that is. They want no more than 4.3 defects per million opportunities. How many opportunities on an automobile are there for defects? More than 1 million. Every screw, every, bearing, every paint job, plastic covers on your headlights. There's probably, let's say you had 1 million opportunities for defects on an automobile. This would say we want the defects to be less than 4.3. And that's pretty good if a defect is like a little scratch on the bottom of the bumper. Okay, you can have 4.3 of those on average, and that would be about the best kind of quality you could ask for. So if your automobile has 10 million opportunities for errors, then you probably have 43, even in the best case, 43 defects on that automobile. Okay, you just hope that they're not critical. And then, so final comments, precision is very satisfying, but we haven't done anything about accuracy. So there's a temptation to just look at the average, right? So, I mean, this is perfect. This is good accuracy and good precision right here. Okay, they're both on the bullseye, so that's accuracy. And they're tight grouping, so that's precision. So this one is precise, but not accurate. So poor accuracy. And this is the tungsten example that I used. If we took the average of those measurements, we might get a value if this is our X bar, we measure it, and we say, hey, we got a bullseye. Okay? But we have such poor precision, we have zero confidence in that result. And so you can never have good accuracy with poor precision. Even though it's like a 2x2, you know, you can have good accuracy, good precision, poor precision. And you might think you could have all four of those blocks. But the one that says good accuracy and poor precision is not a valid block, because you can't say anything confident if you don't have good precision. So precision is something we can work on very well. And we can sort of test ourselves with standards to test how well we get the right answer. But for a true unknown, we really don't know the right answer. But we can be confident when we have good precision. And if we can detect a bias with standards, then we can correct for that. And so if we have a standard, our standard is telling us it should be here at the bullseye. And we consistently measure, and we consistently get this block right here. Then we can correct our instrument and we can calibrate it. So that's what we're doing with calibration. We're measuring our standards, and then we're taking out those biases. This reminds me of a joke. So a chemist, a physicist, and a statistician are going hunting. And you know, they're not the greatest hunters, but they're team up, and they're sitting in the deer stand, and there's a deer at the feeder, and the chemist shoots, and he misses 2 feet to the right. And then the physicist says, I'm next. So he shoots, and he's 2 feet to the left, and the statistician says, we got him. Come on. Right? Because that's this example here, right? You didn't get him. Okay? You think you got him on average, but you didn't get him. Anyway, the right answer is the right answer. And so. All right, so there's some supplemental information here. Let's go through some more problems with the examples of propagation of uncertainty. So I think this will be helpful for you in that period when you're doing a calculation and then you're like, okay, now I need to propagate the uncertainty because DW asked me to do that on the homework, and I don't know which equation to use. And so this is going to help you with those. So here's a standard dilution problem. So we buy a 1 ml standard, and it contains 1 milligram per mil of whatever our standard is. So there's 1 milligram dissolved in 1 ml of a standard, and it's used to prepare 1,000 parts per billion stock solution. And a syringe was used to transfer 250 microliters of that 1 ml. So we've just pulled out 250 microliters, stuck it in a 250 ml volumetric, and diluted to the mark. Standard deal. So we got, 3/4 of our standard left. We stick it back in the fridge. Okay, so what's our uncertainty in that? We're going to calculate that it's 1,000 parts per billion. So we did the dilution correct, but how certain are we in that final stock solution? That's going to be very important, because then if we use that stock solution in a subsequent experiment, we're bringing 1,000 part per billion solution into our standardization or whatever we're using it for, but we also have uncertainty with it that we're bringing in with it. Now look how I've got all these different things here. I've got this parenthesis. Does everybody know how to use this or how to read that? That's telling me my uncertainty. So we're going to call this first number A, and so look at our uncertainty. It's given as 0.01 milligrams per milliliter. Where did that 0.01 come from? It's given right here. So this parenthesis tells you what place value the uncertainty is in. It's in the very adjacent place value. So I can say that, so for this standard, mu is 1.00 and sigma A is equal to 0.01 milligrams per mil. It doesn't have to be 1. What if it was, let's do 1.00, and in parentheses I'm going to put 1.5. Now I've got 2 digits there. Since I have 2 digits of uncertainty, I'm going to have to replace the previous 2 digits. And so my sigma here will be 0.15 milligrams per mil. So do you see how to use the parenthesis method of of uncertainty. That's a great and easy way to present those uncertainties. It's very compact, okay? You don't even need the plus or minus, that's implied, okay? And that's what you'll see if you go on to NIST or CRC or whatever, you look up your standards like Planck's constant, Avogadro's number. You'll have, 8 significant figures and then parentheses and a couple of numbers in there. And this is what they mean. So now just for grins, I calculate the RSD for that. So here's our RSD, the relative standard deviation. I don't know, I've never written out the equation maybe, so okay, so RSD is equal to sigma over mu. Okay, and so here we have 0.01 for our sigma and 1.00 for mu. So this is our relative standard deviation, and it's always unitless because the units cancel. 0.01 milligrams per mil over 1 milligram per mil. And then it's typically useful to think in terms of percentages. So CV is RSD times 100%. So 0.01 times 100%, that's 1%. And so that's our uncertainty in our standard, plus or minus 1%. I would say not great. I would like it better than that, but anyway. That's what we have. Now the 250 mil, let's look at the green number. It's given an uncertainty in terms of percent. And so now that's going to have to be assumed to be the CV. The CV stands for coefficient of variation. Let's see, I haven't written that anywhere either. So CV equals coefficient of variation. Okay, CV. So I'm assuming that this parenthesis number beside the 250 is my CV. So I'm going to go ahead and I'm going to just label it CV. That's equal to 100% times the RSD. So my RSD is that divided by 100%. And so it's 0.005. So there's my RSD right there. Okay. And then if I wanted to calculate my sigma B, the RSD is equal to sigma over mu. So my sigma B is up here, my 250 mils. So I'm going to bring that 0.05 times 250 microliters. That gives me my sigma B. So here's my uncertainty in this 250 microliters. So this takes a little work. If you're given a CV, you've got to divide by 100%, and then you've got to figure out, multiply it by the mu, and then you get your uncertainty. So there's my sigma B. And then the same thing for this volumetric flask. So 250 mil volumetric flask, plus or minus 0.03%. That's a really good one. And so then doing the same calculation, I get my sigma C, my uncertainty in my volumetric flask of 0.075 mils. That's very good. We'll see why in a second. Okay, so this is a skill you need to be able to do. You need to be able to go from CV to the uncertainty or from the uncertainty to the CV. We've done it both ways. This one went from uncertainty to CV and RSD on the way. And here, these were both CVs, and we got to the uncertainty by going to RSD and then multiplying. So that should be automatic for you. There's no question on these about which equation to use or anything like that. You just need to know those definitions of CV and RSD. So now let's calculate our stock solution. So here's our M1V1 equals M2V2. So our dilution equation. So here's our pieces, our two volumes. The 0.25, that should be micro. Oh no, it was 250 microliters, so that's 0.25. So 250 microliters is equal to 0.250 milliliters. So I did a little unit of conversion there just to save some time. And so then we've got our 0.001, that's the result. And I've got mgs per mil, and then I have to do this right here. This is important. Density of water. It sneaks in there. Whenever we're using things like parts per billion or percent, the units on top and the units on bottom have to match. So it needs to either be by volume or by mass. And so this is parts per billion by mass. If it was not stated, it's assumed, but it's parts per billion by mass. And so we need a mass on top and a mass on bottom. We can't have milligrams per milliliter because the milliliter is not a mass. Okay, we've got a mass and a volume, and we don't want to do that in terms of percentages or parts per billion or percent by mass. So what do we want to do? We want to get rid of that milliliter by using the density of water. Now, if these solutions are not in water, then you have to use the density of the solvent. Like if you're using acetonitrile or something like that, you have to take into account the density effect. That's a thing that trips people up all the time. Okay, so it's an important piece. I should probably make this red or something. I'll put a big box around it. Okay. Because now we have milligrams of standard and milligrams of solution. So this is canceled. Okay. Now I want to get rid of that milli. Okay. And so it's already 0.001. I got to put 3 more zeros on there to get rid of that milli, because milli is times 10 to the minus 3. Okay, so I've moved that 3 decimals over, and so I have this many grams of standard per gram of solution. You see why I want to use parts per billion? Because that's a pain in the rear to write. Okay, all these zeros. And so I multiply it by 10 to the 9 parts per billion. Where did the 9 come from? That's billion. Okay. This is no different than multiplying by 100%. 100 parts per 100. A billion parts per billion. What about million? 10 to the 6th. A million parts per million. So we're moving this now to the right 9 decimal places. And so we end up with 1,000 parts per billion. So this piece right here, I think everybody can do up to this piece, but this piece right here is what baffles many people. So work on this. Everybody can get to this number right here with the units, but then you want to deal in parts per billion. That's the piece that I think people struggle with at your stage. Okay, so now the uncertainty. Okay, we have, it's multiplication and division. We don't have any other additions or anything like that, so this should be straightforward. We have our Y result, our 1,000 parts per billion, right here. And then we have the RSDs for all of those. So this is why we needed those sigmas. We couldn't use the CVs. We had to get the sigmas for all of those. So we have the sigmas for all 3 of those measurements or pieces, and then we have the results. So this is going to give us 11.2 parts per billion. So this would be our stock solution, 1,000 plus or minus 11 parts per billion. It's not the greatest, but it, again, 1% error, plus or minus. I wish I had a stock solution that was maybe 1,000 parts per billion plus or minus 1 part per billion. So I would like 0.1% error, not 1% error. How could I approach it? Which of the pieces? I have 3 pieces in this dilution. Which one is hurting me? Which one is hurting me? Which one is making my uncertainty 1% instead of 0.1%? What? The syringe is a good idea. Let's look at the syringe. We've got it right here. The syringe here, this is the CV, it's 0.5%. So it's not quite at 0.1. I would like 0.1, but it's at 0.5. The volumetric flask, it's at 0.03%. Okay. This one is 1%. So it's the original standard, what I bought from the company, which I should have done a better. No wonder that catalog said the other one was more expensive, right? Right. So I bought the cheap standard, plus or minus 1%, and now I got to deal with what I bought. Okay. Now we can see that here too. These are our ratios. These are our RSDs, and we can see, if we just look at this, this is 1 in 100, so that's 1%. Anybody see that? This is 1 in 250. So if we just get rid of those and just look at it, 1 out of 250. This is 1 out of 100. I know that one's bigger. This is 0.08 over 250. So 8 out of 25,000. So my volumetric flask is great. Yeah. So this one is fantastic. Again, that's 0.03%. 0.03%. This was 0.5%. I'm going to have to deal with that too. The syringe is not what I'd like. If I want 0.1%, I'm going to have to get a better syringe. But it doesn't make any sense to buy a better syringe if I'm not going to spend more money on my standard. So that's what this uncertainty analysis gives us. It gives us what we have in our stock solution. That's great. That's useful. But it even more importantly tells us where our problems are in our whole technique if we know the individual components of uncertainty. And so that's what we call a measurement system evaluation. We have our measurement system, we're evaluating each piece, the standard, the syringe, the volumetric flask. And we're looking to see which one of those is the most uncertain. And that's the thing we want to attack. Here's some quick examples. We don't have to go through these in such great detail. But here's anytime you're measuring two things, like two volumes, two masses, we use the straight, sum of variances and take the square root. And so if you've got, plus or minus 0.05 mils on the tick marks, that's not your uncertainty in your result. Your uncertainty result is 0.07 mils, okay? Because it's 0.05 squared plus 0.05 squared. Take the square root. It's not 0.1. It's not that bad, but it is bigger than 0.05. It's 0.07. Here's a log example. So we might use a pH pen, okay? And so we make a solution of 0.1 molar HCl. We do it pretty well. We have a 5% uncertainty in that. Is that right? Yeah. And so then, so here's our calculation. So we measure the log as 1, right? 0.1 molar acid. You take the minus log of that, you get 1. And well, what's our uncertainty? So here's the uncertainty that we have. So our concentration, RSD would be that sigma A over A. And we put those in, and this would be our result in terms of our uncertainty, 0.022. So this would tell us where to round from that pH pen measurement. And so our pH would be 1 plus or minus 0.022. So that's pretty good. And so our CV is 2%. So here's a log example. You got to take into account that log base 10 conversion. And so there you have it. And then the anti-log example. What if we use our pH pen and we measure pH of 1 plus or minus 0.02, not 0.002. So here's our calculation of the concentration of HCl. So it's 10 to the minus pH, so that's 0.1. And then here's the calculation from that uncertainty page with all those equations, doing the anti-log example. And so we end up with an uncertainty of 0.0046. So that's not too bad. Our uncertainty is 4.6. So our cheap pH pen, plus or minus 5%, that's pretty good. And maybe that's what you need. That may be good for you, good enough for you. And so those are my examples, and we're right on time. Okay, even though I got here late, so talked fast, I guess. Look at the homework, get ahead of it so that you're not waiting till the end of the week. And bring your questions on Thursday. I'll see you then.